Hello everyone. We are going to spend the next two videos talking about something called groundwater sustainability. And this is part one, and in this part we are going to define groundwater sustainability and talk about some of the consequences when you have a lack of sustainability. So our objectives are: one, understand the basic concept of groundwater sustainability, what it is, be able to define something called perennial yield, safe yield, sustainable yield. These are terms that are used interchangeably. And as I mentioned, understand the negative consequences of unsustainable groundwater use. In both this video and the next one, I'm going to be relying quite heavily on this outstanding publication from 1999 from the United States Geologic Survey, Sustainability of Groundwater Resources by Ali, Riley, and Frankie. Just a really well-written book. Walks through all the basic concepts associated with groundwater sustainability and how you go about analyzing it, and talks about the different consequences and so forth. So, what do we mean by groundwater sustainability or sustainable groundwater use? This is the definition from the book, from the previous slide. The development and use of groundwater in a manner that can be maintained for an indefinite time without causing unacceptable environmental, economic, or social consequences. So another term for it is safe yield, sustainable yield, and perennial yield. Now let me qualify that. These terms are referenced in the context of how much water you can withdraw from the aquifer and still maintain sustainable conditions. Another classic definition of perennial yield is the maximum amount of water of usable chemical quality that can be withdrawn and consumed economically each year for an indefinite period of time. Perennial yield cannot exceed the natural recharge to an area indefinitely, and ultimately is limited to the amount of natural discharge that can be salvaged for beneficial use. So let's unpack this a little bit. In the first part, maximum amount of water of usable chemical quality. In most aquifers, if you go deep enough, you will encounter saline water. It's older water. And sometimes it has so much salt and other chemicals in it that it is no longer, or that it's not a viable resource for municipal or agricultural use. Or this can refer to pumping water, near a coast or an ocean where you can get salinity intrusion, which we'll talk about. Consumed economically, if your water table is too deep, it takes a lot of energy and money to pump it up to the ground surface, so that can be prohibitive. And of course, perennial yield cannot exceed the natural recharge. That's a basic water balance issue. You cannot take more water out of the aquifer than is naturally recharged or put into the aquifer. Really, that's the core concept that we're talking about here in terms of sustainability. Now that might seem pretty simple, but it turns out that trying to quantify how much water, what your water balance is in an aquifer is not trivial. You don't know for sure what the recharge is. So there's a lot of guesswork involved. Testing and analysis and groundwater modeling can be really important. And it's even more complicated. The part highlighted in red is ultimately limited to the amount of natural discharge that can be salvaged for beneficial use. And this probably won't make the most sense until you get through the end of the next video. But basically what that means is it's possible, even if you knew exactly how much the recharge is, you can't necessarily pump that much out. It depends where the pumps are located, and it depends on the overall aquifer dynamics. It is possible that you could, if your wells are in the wrong location, you may end up having to pump all of the water out of an aquifer before it ever gets balanced with the recharge. And so again, by the time we get through the next slide, this will make more sense. But for now, just think of unsustainable use as pumping more groundwater out than is naturally being supplied into the aquifer. Now, aside from the obvious fact of you're going to run out of water eventually, what are some of the negative consequences associated with unsustainable groundwater use? And one of the more significant ones is aquifer subsidence. So let's suppose we're looking at a section of our aquifer, and this is our water table, and if we pump too much over time, if we're pumping more than is naturally being recharged, the water table could drop, and in some cases it could drop substantially. 100 meters or more is not unheard of. And when that happens, when the water table drops, the pore pressure in the aquifer decreases. And when that happens, if the pore pressure decreases, the effective stress, or the interparticle stress in the aquifer matrix, increases. And if you've had an introduction to soil mechanics, you know that the effective stress, sigma prime, is equal to the total stress minus the pore pressure. So if the pore pressure goes down, the effective stress goes up. Intuitively, the water table drops, you're losing some of the buoyancy effect, and so gravity weighs more heavily on that aquifer matrix, and it causes it to compress. And so that effectively shrinks, squeezes the aquifer like a sponge, and that can lead to a permanent compression of the aquifer. And, well, you say, what's the big deal? If the water table goes down, if it eventually goes back up, everything's okay, right? Well, it turns out that most aquifers, or many aquifers, if they have a significant clay or silt content, this compression is non-elastic. And what that means is, if you refill the aquifer, increase the pore pressure, thereby decreasing the effective stress, get back to where you were before, it doesn't expand to its original state. That lost void space is only partially recovered. So that capacity you had for the aquifer is permanently lost. There's less void space in the aquifer. Furthermore, when we talk about aquifer compression, the result of that is the ground surface drops. The elevation of the ground surface drops. And I have some slides illustrating that. This is a site in Turkey that had significant groundwater withdrawals, so much so that it had some major subsidence, and this can have a significant impact on your infrastructure, roads and pipes and buildings. Mexico City, in some places, has had many meters of subsidence and damage associated with that. Taipei, Taiwan is another one that's had a lot of subsidence. There's been a lot of pumping in southern Arizona, and this map shows the brown and pink regions, there's a water level decline of greater than 100 feet, which is about 30 meters or more. And the pink areas, there's significant groundwater subsidence in these areas. Las Vegas, Nevada has some of these same issues as well. This is also from southern Arizona. It's so bad in some places that they'll have signs warning of groundwater subsidence, and they can have actually had fissures open up as a result of overpumping of the aquifer in this region. This is another one from southern Utah, Cedar Valley. In southern Utah, there's been a substantial overpumping of groundwater, and you can see the contours. There are contours of subsidence in Cedar Valley, and I'm not sure if those are meters or feet, but there's a substantial amount, and in some cases it has resulted in damage, as shown on the left. Another famous case is in the San Joaquin Valley in California. This has been corrected. The groundwater there is being managed more sustainably, but historically they had significant overutilization of groundwater and significant groundwater subsidence. You'll see this map shows where that was most highly concentrated, and there were areas where there's more than 8.5 meters of subsidence. And this is a fairly famous photo from the San Joaquin Valley, and the markers on this pole show where the ground surface elevation was in 1925, 1955, and 1977 for this particular area. So you can see the groundwater subsidence can be really dramatic, and definitely something we want to avoid. Another negative impact is saltwater intrusion. In a normal system where you have fresh water next to the ocean, when water has salt in it, it has a higher density, it weighs more, and so the lighter fresh water floats above the salt water, and we call this a freshwater lens. And as recharge comes in from the left, and as long as you have a gradient of groundwater from the left to the right or towards the ocean, that freshwater lens will float above the salt water, and there will be a source of fresh water for wells that are near the ocean. But if there's too much pumping and that freshwater lens gets thin, that salt water will start encroaching back to the left and eventually could be captured by the wells. And this is illustrated further on the right. This is a site showing we have equipotential lines. So the black lines are head contours, and you'll notice -20, -30, -40. The groundwater levels actually go down as you go inland. So what's happened in this spot is they've been pumping the water so much that they've reversed the groundwater gradient, and so the salt water then is encroaching and migrating inland. And you can see at the top there's a graph of saltwater concentration versus time at a selected location somewhat in from the coast here. This is a significant problem in a number of regions around the world, and it requires groundwater to be very carefully managed near coastal areas. Florida, in southern Florida, there's a multi-billion-dollar citrus industry, and the whole state of Florida is extremely flat, so you don't have to vary the water table elevation much at all to get a reverse gradient for the salt water going in. And so in southern Florida, they have a network of canals to artificially recharge the groundwater as needed to make sure that they keep that right gradient and they don't have saltwater intrusion. So this is a really important thing, and again, it has to do with if you're pumping more water out than is naturally being recharged near the ocean, you will eventually have a problem with saltwater intrusion. And finally, drought mitigation. Groundwater represents a massive underwater reservoir. And so when we have a drought, groundwater is used to make up for the lack of surface water available. So this reservoir on the left is a reservoir in California during a significant drought period. So when we have a drought, we pump more groundwater. It's a great buffer or resource to use. But if we overdo it, we could theoretically get to the point where we have depleted groundwater resources, and then we hit a massive drought, and we no longer have that buffer available, and then we're in real trouble. And this is something that's increasingly important as one of the impacts of climate change. We're seeing really significant droughts. At the time of this recording, in the state of Utah here in the western United States, the last few years we've been in what they're calling a 1,200-year drought. And so this can be a really big problem if we're not careful. We could deplete our groundwater resources, and as the drought continues or as we encounter another drought, we could be in big trouble. And so we need to manage our aquifer sustainably so that we don't have groundwater subsidence, no saltwater intrusion, and that resource is left to future generations to manage or to meet their water needs and to be a backup in case of drought.